class. So whoever is ready, share your screen and we can start.
Okay. Yeah, question 4.63. It's Poisson random variable questions, which is 4.7 chapters. They give the formulas here. There's a formula.
Okay, you're ahead of us. We haven't talked about Poisson yet, but go ahead.
I have learned this in like the different class. So
Great. Go ahead, teach us.
it's the number of times that a person contract a code in a given year is a Poisson random variable with parameter lambda 5. Suppose that a new wonder drug based on large quantity of vitamin C has just been marketed that reduce the Poisson parameter to lambda equal to 3 for 75% of the population. For the other 25% of population, the drugs has no appreciable effects on codes. If an individual tries the drugs for a year and a half, has 2 codes in that time, how likely is that the drugs being beneficial for him or her? So we know that A beta drugs has effect, then the drugs have no effect 0.25%. And then given that it's a year test of 2 codes in that time, so 2 of the drugs has effect, it's by the formulas, I just plug in the numbers. For that, for lambda is 3, because lambda equals 3 for 75%, that's like has the effect. And then plug in 5 for the ones that doesn't have effects. And then I do this one to find out that the drugs it's like benefit of the 2 codes. It's probability of the 2 codes of a drug has effect, and the probability of the drug has effect over the whole probability, which is 9 out of 2 to the to the negative 3 powers, and times 3/4 for the ones with the effects over the whole probability, which is 0.8886.
Finished?
Yeah.
All right.
Do you guys have any questions?
I'm trying to see this. Okay, it looks good to me. I don't have any questions. Anyone else has any questions?
Yeah.
All right, great.
Okay.
Thank you, Paul. We're going to talk about Poisson random variables today.
Good evening.
Good evening.
Can you see my screen?
Yeah.
So I'm going to present question number 50 from chapter 4. So the question is, when coin 1 is flipped, it lands on heads with probability 0.4. When coin 2 is flipped, it lands on heads with probability 0.7. One of these coins is randomly chosen and flipped 10 times. A. What is the probability that the coin lands on heads on exactly 7 of the 10 flips? So in here, I use X to represent the number of coin 1 lands on head, and Y to represent the number of coin 2 lands on head. So we use the binomial function. So it's probability of X equal to 7, which is 10 choose 7 times the 0.4 to the power 7, and times 1 minus 0.4, which is 0.6 to the power 3. Then make a calculation which is equal to about 0.04. And the probability of Y equal to 7 is 10 choose 7 times the probability that 0.7 to the power 7, and times 1 minus 0.7, which is 0.3 to the power 3. Then make a calculation is 0.27. And also we need to randomly choose one coin from these two coins. So the probability of coin 1 be chosen is equal to the probability of coin 2 be chosen, which is 1/2. So the probability of exactly 7 heads of 10 flips is equal to 1/2 times the probability of X equal to 7 plus the probability of Y equal to 7. Then make a calculation is equal to 31 divides 100. And B, given that the first of these 10 flips lands heads, what is the conditional probability that exactly 7 of the 10 flips land on heads? So I use A to represent the event of exactly 7 of the 10 flips lands on heads, and B to represent the event of first flip lands on heads. So the conditional probability of A given B is equal to the probability of A intersection B divides the probability of B. So in here, the probability of A intersection B, which is equal to 1/2 times 1 choose 1, because we need the first flip lands on head. So it's 1 choose 1, and we still have 6 head left. It's chose from the 9 time. So it's 9 choose 6 times the 0.4 to the power 7 and times the 0.6 to the power 3. So that's the coin 1. So the coin 2 is similar, that 1 choose 1, 9 choose 6, and times the 0.7 to the power 7 times the 0.3 to the power 3. And the probability of B is equal to 1/2 times 0.4 plus 0.7, which is come from here. That's the coin that lands on heads with their probability. And we just plug in these two into the equation. Then make a calculation, we will get the answer is 0.1977.
Great. I always like some girls work in our class. Very clear. Okay, very good showing. Thank you.
You're welcome.
Can you see my screen?
Sorry, I
Can you
muted. Yes.
hear me?
Yes.
Okay. This is question 46. A student is getting ready to take an important oral examination and is concerned about the possibility of having an on day or an off day. He figures that if he has an on day, then each of his examiner will pass him independently of one another with probability 0.8. Whereas if he has an off day, this probability will be reduced to 0.4. Suppose that the student will pass the examination if a majority of the examiner partners pass him. If the student believes that he is twice as likely to have an off day as he is to have an on day, should he request an examination with 3 examiners or with 5 examiners? So we let the x be the times passed the exam. Since the test result can only be either pass or fail, so we can apply to the binomial random variable. And for the first part, we let the examiners be the n, so n will be 3. And since the event, and we have 2 possible cases, the test is taken on the on day or off day. So for the event would be the sum of event that happens in the on day and on the off day. So for this part, so basically we have x equal to 0 to 2, 3. That's when we have 3 examiners. And we just apply the formula on here. And then for this part, that's on day. And for this part, that would be the off day. And then since, and also the on day, the off day is twice likely to have he is twice as likely to have an off day as he is to have an on day. So the probability to have an on day is 1/3, and off day is 2/3.
That's right.
That's why we have 2/3 here and 1/3 here. So this represents the on day, and this represents the off day. And then we only consider when x equal to 2 and x equal to 3 because the student passed the exam. We pass the exam if the majority of the examiner pass him. So out of 3, we only need 2 or 3. When the x is 1, when he only pass 1 exam, that means 2 fail. That means he won't pass the exam. So we only consider the case when x equal to 2 and x equal to 3. And the sum of the possibility would be 0.533. That's when that's the probability when there's only 3 examiners. And similarly, when there's 5 examiners, we do the same thing, but we only consider when x equal to 3, x equal to 4, and x equal to 5. And we have the possibility of 0.525. Since 0.533 is greater than 0.525, so the answer is it's better to take the exam when there's 3 examiners.
Yeah, very nice. Very nice. Anyone has any questions? Yeah, great. You see your own mistake. You correct yourself. That's great. Thank you. Thank you, Jie.
Excuse me.
Yeah.
Yes, I know right now. Yeah, sorry, I'm not home right now. Sorry if you hear something in the background. So I'm doing number 43. A and B will take the same 10 question exam, and each question will be answered correctly by A with 70% chance, independent, and with person B by 40% chance, independent. So the question is asking to find the expected number of questions that are answered correctly by both A and B. So this is a binomial random variable problem. And the way you find expected value for this is the number of trials times the chance of success. So if we let C be the event that they both get the question right, the probability is a union of A and B, which is 0.7 times 0.4. which is 0.28. And the expected value of C will be the number of trials, which is 10, times the probability of it, which is 0.28. So the expected value is 2.8 for them to get questions both right for a 10-question quiz. Part B is find the variance of the number of questions that are answered correctly by either A or B. If you let event D be the questions that either of them gets right, which is the union of A and B, the probability would be 1.1 minus 0.28, which is 0.82. Oh, sorry. The way you find variance in a binomial random variable problem is NP times 1 minus the probability. So if n is 10, probability is 0.82, and 1 minus p is 0.18. If you multiply, you get 1.476 is the variance of either of them getting a question right.
Great. That's a
Sorry
good review.
about background noise. Did you hear anything
It's
about
okay.
that?
It's okay. It's a great review for last class. So with a binomial random variables, we have these nice formulas to follow. Expected value equals the number of trials multiplied by the probability of the success. Then variance equals to the number of trials times the probability of success and the probability of the failure. And so this is 1.1. 1.1 comes from 0.7 plus 0.4. All right, so for A is 0.7, probability for B, probability is 0.4. So he adds up, the formula is the probability of A plus probability of B minus probability of A and B. So that's what he applies here. So 1.1 minus 0.28. Great, Rob, thank you. Good review for last class.
Thank
you. Good evening, Professor. I'm going next.
Okay, Sarah.
Yes. Professor, can you see my screen?
Not yet. Yes.
No?
Yeah, now.
I'm going to present question number 44. A communications channel transmits the digits 0 and 1. However, due to static, the digit transmitted is incorrectly received with probability 0.2. Suppose that we want to transmit an important message consisting of one binary digit. To reduce the chance of error, we transmit 5 zeros instead of single zero and 5 ones instead of single one. If the receiver of the message uses majority decoding, what is the probability that the message will be wrong when decoded? What independence assumptions are you making? So, for this question follows a binomial distribution. Binomial distribution is used where the probability P of success is constant for each trial. A random variable x is a binomial distribution if it uses non-negative value and its probability mass function is given as. This is the probability mass function in which we have x varies from 0 to n and q is equal to 1 minus p, which is probability. Otherwise, n and p are collected parameters of binomial distribution. Probability that a randomly transmitted digit is correctly transferred p is equal to 1 minus 0.2, which we will get 0.8. A series of correctly transmitted bits n number is equal to 5, like we have 5 zeros and 5 1, that's why it's 5. The expected number of correctly transmitted bits, expected number of bits E is equal to n into p. When we will put parameters value, we will get 4. Then we have to find probability that the message is decoded properly. A message will be decoded properly if at least 3 binary digits are transmitted correctly. Probability into x greater than equal to probability of x greater than equal to 3, which is equal to probability of x greater is equal to 3 plus probability of x is equal to 4 plus probability of x is equal to 5. Then when we will put the values of these probability, we will get the answer 0.942 after calculation.
Wow, 94%. Great job. I like this. Yeah.
Thank you, Professor.
I like this. Yeah, very good review for last class. Anyone has any questions? Thank you, Ikera. Very good.
Okay. Okay, Professor, thank you.
Yeah, good presentations. Tom.
Okay, for this question, we're comparing the Poisson approximation with the binomial probability. So we have to find lambda, which is the mean, which is number of trials times probability. So NP gives us our lambda value. And after that, it's just kind of a matter of plugging in. I would be the value for the random variable. So that's the Poisson in a nutshell. For the binomial distribution, kind of similar in that we're given n trials, I is the number of the value for the random variable, p to the I is the success, and 1 minus p is like the failure to the n minus I. And now after calculating all this stuff, we get, as a summary, the binomial distribution tends to the Poisson distribution as n goes to infinity and p goes to 0. So the Poisson distribution closely approximates the binomial distribution if n is large and p is small.
Interesting, huh? Interesting. All right. Yeah, I guess you wrote a lot more than what you said, but that's okay because I haven't even talked about Poisson random variable yet. So yeah, you guys are ahead of me. Okay, it's good. Thank you.
Hi, Professor.
Hello, Zakia.
Hi. Can you see my screen?
Yeah, are you going to do 48?
48, yes. Thank
Okay.
you. So
You're
the
welcome.
question is, in some military courts, 9 judges are appointed. However, both the prosecution and the defense attorneys are entitled to a peremptory challenge of any judge, in which case the judge is removed from the case and is not replaced. A defendant is declared guilty if the majority of judges cast votes of guilty and he or she is declared innocent otherwise. Suppose that when the defendant is in fact guilty, each judge will independently vote guilty with probability 0.7, whereas when the defendant is in fact innocent, this probability drops to 0.3. So we have to find what is the probability that a guilty defendant is declared guilty when there are 9, 8, and 7 judges. We have to repeat the same thing for an innocent defendant too. So we know that the probability mass function of a binomial random variable having parameters n, p is this formula where I equals 0 to n. So we have given that the the probability of when the defendant is guilty, each judge will vote guilty is 0.7. So, which is the vice versa of um, so we gonna have voted innocent 1 minus 0.7 because the total probability is 1. So when we have the given probability of voted guilty is 0.7, the other one should be 0.3. And then we have also given that the innocent one is the defendant innocent voted guilty is 0.3. So the other one will be, the voted innocent will be 1 minus 0.3, which is 0.7. So we have to find probability for that a guilty defendant is declared guilty when there are 9, 8, and 7 judges. So when n equals 9, we're gonna use this formula, the probability mass function, and we're gonna do summation from I equals 5 to 9. So at least 5 up to 9. And we're gonna do summation for each of them. So which is 9, where we're gonna put I equals 5, and then 0.7 is the probability given, and here 0.3 is 1 minus p, which is 1 minus 0.7, and n equals so n equals 9 minus I is 5 over here, so 9 minus 5 is 4. So we're gonna do same thing for each of them. So when I equals 5, 4, 3, sorry, when I equals 5, 6, 7, 8, and 9. Yeah, we are going up. So the total is gonna be 0.9012. We are doing same thing for n equals 8 and 7. So for n equals 8, we're gonna have up from 5 to 9, at least from 5 to 9, and for n equals 7, we're gonna have from 4 to 9, 4 to 7, 4, 5, 6, 7. So I just skip the summation over here. We're gonna do the same summation I did for
Yeah.
n
Yeah, we
equals
understand.
9. Yeah. So I just skip that. Now, for question B, we have to do probability for innocent person who voted guilty. This one we have done for guilty, voted guilty. Yeah. So it's the same thing. Here we have the probability given is 0.3. So we're gonna write, we're gonna put 0.3 here, and so 1 minus 0.3 is gonna be 0.7 for this part.
Yeah, basically we just switch the idea of success and failure. So for B, the success is innocent. For A, the success is guilty.
Yeah, exactly. Yeah. So yeah, that's it.
Okay, great.
Yeah,
So
thank
no
you.
comparison, right? Just calculation. All right.
Yeah,
Okay, thank you, Zakia.
thank you.
Hello.
Hello.
All right, so I did problem 50 from chapter 3.
Okay.
For this problem, it's each of two cabinets identical in appearance has two drawers. Cabinet A contains a silver coin in each drawer, and cabinet B contains a silver coin in one of the drawers and a gold coin in the other. A cabinet is randomly selected, and one of its drawers is opened, and a silver coin is found. What is the probability that there is a silver coin in the other drawer? So I have denoted A, B cabinet A, B cabinet B, C be the silver coin. And so what we have known is that the probability of A and B is equally likely to be chosen. So it's going to be 1/2 for each of them. And then for C given A, it's going to be 1 because there's a coin in all drawers. And we have C given B 1/2 because there's a silver coin in one of two drawers. So you apply the Bayes formula here because we have mutually exclusive events. For the probability of B given C, I believe that can actually be ignored, and we could just focus on the probability of A given C. So pretty much you just plug in the probabilities into the equation, which gives us 2 out of 3 as the probability there's a silver coin in the other drawer.
What's the probability of a silver coin drawn from cabinet A, right?
Yeah, well, yes, but they're equally likely to be chosen, right? So
Traceria notation is probability of a silver coin drawn from cabinet A. Then the second one is a silver drawn from cabinet B. So it's 1/3 and a 2/3.
Yeah.
I see. Okay, nice. But we are in chapter 4.
I know. I haven't done a problem in chapter 3.
Good
Next class I'm gonna do a problem from chapter 4.
Okay. All right. Thank you, Adarius.
Yeah, thank you.
Hello.
Hello.
Hi. I think I'm next.
Okay.
I'm doing 4.74.
Oh, okay. That's far. 74.
Yes. It says consider a roulette wheel consisting of 38 numbers, 1 through 36, 0 and 00. It says if Smith always bets that the outcome will be one of the numbers 1 through 12, what is the probability that A, Smith will lose his first 5 bets, and B, his first win will occur on his 4th bet? So for this question, we're using the binomial distribution, which is P. X equals P to the power of X times Q to the power of N minus X, the formulas. There are 38 numbers on the wheel, but he bets from number 1 through 12. So the probability of him getting a successful bet is 12 out of 38. 12 numbers out of 38 numbers. I reduced this to 6 out of 19. And then to find the probability of him losing a bet is, which equal Q, is 1 minus the probability of winning a bet, successful bet. So 1 minus 6 over 19 is equals to 13 over 19. And so for question A, the probability that he will lose his first 5 is the probability that he will lose 1 to the power of 5, which is 13 over 19 to the power of 5. 0.15 is the answer for A. And for B, it says his first win will occur on his 4th bet. For this one, you have to use the...
Hold on a second. Let me ask you this. Yeah. You were talking about this is a binomial random distribution.
Yeah.
How do we calculate the probability of binomial random distribution?
You said, sir?
Right. Probability he will lose his first 5 bets.
Yes.
How do we calculate this? This is a binomial distribution. You showed us the formula before, right? Did you? If you go up, yeah, right here.
P,
probability
P,
of X.
P, yeah,
right.
and then Q is not P, or 1 minus P.
Right. So you need to do that. You need to follow this formula. So probability of losing. So now you can think the losing bet is a success. So you have probability of X equals to 5.
Right.
Right. So you need to do out of how many is so what is N?
Pardon, sorry?
Because I was thinking you need to use the binomial, right? Binomial formula. So how many times he played? Let's see. If you go up, you keep going up.
It doesn't say how much he plays.
Oh, it doesn't say. It doesn't say. Okay, it does say you lose first. Hold on a second. With Smith is always the best, and I can be one of them. Lose his first 5 bets. We don't need to apply binomial, but we don't know n. We only know 5. We only know the random variable equals 5.
Is that not because he doesn't place a certain amount of bets? It's just asking.
We can consider the first 5.
Yeah,
So that's why
it's
you're
not,
saying, okay,
yeah,
let's multiply the probability of the losing.
yes,
Which losing is 13 over 19. So that's why you have 13 over 19 to raise to the fifth power. I see, I got it. Okay.
it's 26 over 38, but I just reduced it.
Simplify, right?
Yeah, half of 12 over 38.
Okay.
So
What about
first
B?
5.
Yeah.
First win will be on his 4th bet. So for this one, you're saying that he loses the first 3 and wins on the 4th one. So losing on the first 3 would be the same formulas over here as up here, 13 over 19, but it would be to the power of 3 since it would be 3 losses, and then you would multiply it by a win for the 4th bet, which is 12 over 38 power 6 over 19.
Okay, I see.
And
I
that's the
see.
probability.
Okay, thank you, Anjali.
No problem.
Thank you. Anyone has any questions or comments? All right, thanks. Anjali. Okay, for presentation credits, the highest one is 120 over 100. The lowest one is still 0. So hopefully, oh, Ayat wants to present. Okay, let me make you a presenter. Yeah, go ahead. You're presenting.
Give me a sec. Okay. Okay, the question is 435.
Okay.
2 cards are drawn at random from an ordinary deck of 52 playing cards. If the 2 cards display the same suit, you win $2. If they are of the same color only, you win $1. Otherwise, you lose 50 cents. Calculate A, the expected value of the amount you win, and B, the variance of the amount you win. Okay, for the question A, let's calculate the probability to choose 2 cards of the same suits. So there are 4 suits in the deck. So the probability to choose 2 cards of the same suit out of 52 cards is the probability of choosing number of combination to choose 2 cards of the same suit divided by a number of combinations to choose any 2 cards from the deck. So this probability is 23.5%. So next one is now calculate the probability to choose 2 cards of the same color from the deck. There are 2 colors, red and black. So the probability to choose 2 cards of the same color is the division of number of combinations to choose 2 cards of the same color. This is it.
Oh, hold on a second. Hold on a second. You already have 2 out of 2. Choose 1. So you already have these two colors. Two of the suits. But then here you have 26. Choose 2.
Yeah,
Could
that's
it be
multiplication of 2 events. First event is the choosing red or black, and second one is choosing 2 cards from the chosen color.
Okay.
If you choose like, so that's a probability. This probability equals to the division of number of combinations to choose 2 colors of the same color by number of combinations to choose 2 colors of from the deck. So it's equal to 49%.
Almost 50%.
Yeah.
It makes sense. Yeah.
Mm-hmm. Okay, next part, we have to calculate the probability to lose 50 cents. It equals to 1, which is the total probability, minus 2 previous probabilities, this and this. So it equals to the probability to lose 50 cents is equal to 27%, 27.5. And the expected value of the amount you win is equal to summation of x by the probability of x. So it equals to summation of $2 by probability to choose 2 of the same suit, plus $1 multiplied by probability of choosing 2 colors of the same 2 cards of the same color, minus the multiplication of 50 cents by probability to lose 50 cents. So expected value of the amount you win is 82 cents, actually.
Nice. Yes. Good corrections. Nice.
Yeah. And for the second question B, the variance of the amount you win, you calculate by the formula, this formula. I just use the x squared. So it's $2 squared, $1 squared, and minus 0.5 squared multiplied by corresponding probabilities. Minus EX squared. This is it.
Expected value squared.
It's
okay.
Also.
Yeah.
The variance is 82 cents. Right?
Interesting, huh? Expected value and the variance are the same. This is a good review. I like this. Okay, thank you, Ayat. Anyone has any question? All right. Anyone else like to present?
Hi.
Yes, Anjali.
I asked the question and someone said 1.5 extra. I'm not sure how.
Oh, 1.5
Can you
points extra.
explain?
Oh, okay. So let's see. Let me show you this. Okay, so you see presentation, right? The highest one. So 100, but I have, see here, I have 120. And also I think I have 100. I think I have also have 110. Or maybe I have 100 and 120. All right, how does this work? For 60%, so each 10% is 1.5 points, adds up to your final grades. So what I'm going to do is, for these people, let's see, 120, that's a GA. So he has 20% more. So 20 times 20, so which is 3 points. So these 3 points will be added to his final grades.
Professor.
Yeah.
I got a question. This is like 110 for the attendance for sure.
Oh, that's for attendance. Oh, did I? Hold on 1 second. Let me see. I put in the wrong spot. Presentation. Oh, okay. 秀云, no, 秀云, sorry, 秀云, this is about 90. So I make mistake. So that's how bad my eyesight is. Thank you so much, Hao. Yes, the one I was like, I couldn't find my 110. Okay, let me know whenever I make mistake. Let me see. Oh, Showing also wondering. Yeah, you couldn't have 110 for attendance. All right. So does this answer your question, Anjali?
Yes, thank you.
Okay, so in this way, just keep presenting. All right, keep presenting. Because for this class, okay, share this. As you are learning, I am reviewing, my knowledge, because I've taken probability courses a while ago. And sometimes you guys are teaching me, all right? And I really appreciate, because I have been teaching calculus, college algebra, pre-calculus, linear algebra, so probability is pretty new to me this semester as well. All right, so again, thank you. So let's see the comments. Catherine is saying, so the extra points in presentations is added to final exam grade. Yes. Yes, Catherine. Okay. Now let's go to, so my plan today is to talk about the Poisson random variable, which, some of you have already taught me something. Basically, it's a formula. It's a formula to follow. So let's read this paragraph. And usually, when you do the question will tell you it's a Poisson distribution. All right, it's a Poisson random variable. So here says a random variable x that takes on one of the values 0, 1, 2. So all these whole numbers. If a number starts from 0, 1, 2, we call whole number system. It's said to be a Poisson random variable with a parameter lambda if for some lambda is required to be positive number, and the probability of the value of the random variable is E Euler number raised by negative lambda, then multiplied by lambda raised by the value of the random variable divided by the value of the random variable factorial. All right. So this is introduced by Simeon Dennis Poisson. That's why it's called a Poisson random variable. And a lot of times when we talk about probabilities, we will talk about the Poisson distribution. And of course, the value of the random variable are whole numbers. So this equation defines a probability mass function. So why? Because if we add this up, right? Remember this is infinite series. Infinite series is e to the x, but here the x is a lambda, so this is e to a lambda. And e to a negative lambda times e to the lambda equals e to a 0, which is a 1. Right, because it adds up the probability of the values of random variables adds up to be 1, so it's a probability mass function. Right, I don't know if you can remember this. Right, actually it's not so difficult to remember, right? The e to a negative lambda, and then you know this part. If we do summation of this part, that's e to a lambda. Let's read this paragraph. The Poisson random variable has a tremendous range of applications in diverse areas because it may be used as an approximation for a binomial random variable with parameters of n, p, which Tom showed us, right, in the presentation. When n is large enough and p is small enough so that np is of moderate size. To see this, suppose that x is a binomial random variable, so this comes a little proof. You can read yourself, all right? I'm not going to go through this. So this is a little proof about this statement. In other words, if n independent trials, each of which result in a success which probability p are performed, then when n is large and p is small enough to make an NP moderate, the number of successes occurring is approximately a Poisson random variable with parameter lambda equals to NP. Yeah, in binomial, NP is the expected value. So lambda is, so this value lambda will usually be determined empirically. Let's see this. This is interesting. Some examples of random variables that generally obey the Poisson probability law as follows. So the number of misprints on the page of a book, the number of people in a community who survive to age 100, the number of wrong telephone numbers that are dialed in a day, the number of packages of dog biscuits sold in a particular store each day, the number of customers entering a post office on a given day. Wow, it's interesting, isn't it? It's interesting. Okay. Each of the preceding and numerous other random variables are approximately Poisson for the same reason. Yeah, Poisson distribution is very popular, namely because of the Poisson approximation to the binomial. Let's see this example. For instance, we can suppose that there is a small probability P that each letter typed on a page will be misprinted. Hence, the number of misprints on the page will be approximately Poisson with mean equals this. When n is the number of letters on the page, similarly, we can suppose that each person in the community has some small probability of reaching age 100. Also, each person entering a store may be thought of having some small probability of buying a package of dog biscuits, so on. Interesting, huh? Let's see some real examples. 7a. Suppose that the number of typographical errors on a single page of this book has a Poisson distribution with parameter lambda equals to half. Calculate the probability that there is at least one error on this page. At least one error. We want to look for its complement. So the random variable denotes the number of errors on the page. So probability of x greater than or equal to 1 equals 1 minus probability of x equals 0. Right? So Poisson probability, we just plug into the formula. So we get an e to the negative half, which is this. Let's see, 7b. Suppose the probability that an atom produced by a certain machine will be defective is 0.1. Find the probability, so this is pretty small, right, 0.1. Find the probability that a sample of 10 atoms will contain at least one defective atom. So out of 10, at most one defective. At most one could be none of them or could be one of them. So we want to find the probability of this. So out of 10, choose none. That's just 1. Then 0.1, so defective 0. Not defective 10. So binomial adds up to be about 74%. Whereas the Poisson approximation yields a value of e to the negative 1 plus e to the negative 1. If we plug in 0 for the I, plug in 1 for the I, we get an e to the negative 1, e to the negative 1. It's about the same as the binomial distribution. Interesting. If anyone has any question, let me know. Let's see C. Consider an experiment that consists of counting the number of alpha particles given off in a 1-second interval by 1 gram of radioactive material. If we know from past experience that on the average, 3.2 such alpha particles are given off, what is a good approximation to the probability that no more than 2 alpha particles will appear? How do we know this is a Poisson distribution? Let's see. If we think of the gram of radioactive material as consisting of a large number of atoms, each of which has a probability of 3.2 out of an. Oh, okay, that makes sense now. Okay, so now, yeah, because we're talking about atoms, right? That has to be large. So 3.2 out of this n, it should be considerably small. Of this disintegrating and sending off an alpha particle during the second considered, then we see that to a very close approximation, the number of alpha particles given off will be a Poisson random variable with parameter lambda equals 3.2. Then the desired probability will be x less than or equal to 2, right? No more than 2 alpha particle. Less than or equal to 2. We do the calculation, we just plug in, right? Less than or equal to e to 0, right? X equals 0, x equals 1, x equals 2. Then do the calculation is about 38%. Before computing the expected value and the variance of the Poisson random variable, I was wondering how close that to compare to the binomial. Because lambda is mean now, lambda, right? Comparing with binomial, that's NP. Well, let's see. Before computing expected value and the variance of the Poisson random variable with parameter lambda, we call that this random variable approximates a binomial random variable with parameters n and p, which n is large, p is small, and lambda equals np. Since such a binomial random variable has expected value of np equals lambda and a variance of np times 1 minus p, which is lambda times 1 minus p, it's about lambda because p is small, right? So 1 minus a very small is just 1, so it's about lambda itself. So, interesting, Poisson random variable, so the expected value and the variance might be just lambda. It would seem that both expected value and the variance of a Poisson random variable would equal its parameter lambda. We now verify these results. If we plug in, indeed, nice. So the expected value of a Poisson distribution is lambda, which is mean, and is the variance of if we calculate the variance, let's see, it's ex squared. So ex squared is this. What is e of x squared? E of x squared is lambda, right? E of x is lambda squared. So we have a lambda square plus lambda minus lambda square, which is lambda. All right, so that's what I remembered, because the Poisson distribution, the mean and its variance is lambda. Yes, it's right. Anyone has any question? Okay, so conclusion. The expected value and the variance of a Poisson random variable are both equal to its parameter lambda. Right? Remember, the expected value for binomial is n times p. The variance is n times p times 1 minus p. You want to skip out this. What is this? Let's see. Poisson paradigm. Consider n events with pi equal to the probability that even I occurs. So I equals 1 up to n. So no 0 here. If all the pi, so those are natural numbers. If all the pi are small and the trials are either independent or at most weakly dependent, then the number of these events that occur approximately has a Poisson distribution. Okay, with the mean equals to this as up all the probabilities. Okay, so PI, the PI represents the probability of the random value of I. But PI is supposed to be considerably small. So this should be the lambda. So the n events, and PI represents the probability that even I occurs. And all the PIs are small. And the trials are either independent or weakly dependent. Then it has a Poisson distribution with this mean. It's interesting, huh? So this not adds up to be 1. Our next example not only make use of Poisson paradigm, but also illustrates a variety of the techniques we have studied so far. Let's see. So length of the longest run. A coin is flipped n times, assuming that the flips are independent, with each one coming up heads with a probability of p. What is the probability that there is a string of k consecutive heads? So we will first use the Poisson paradigm to approximate this probability. Now, if for I equals I goes to n minus k plus 1, we let hi denotes the event, and the flips I plus 1, I plus k minus 1, all land on heads. So starting from I until I plus k minus 1, all land on heads. Then the desired probability is that at least one of the events hi occur. Because hi is the event that's starting with the flip I, the next k flips all land on heads. It follows that the p of hi equals p raised by k. Thus, when p raised by k is small, we might think that the number of hi that occurs should have approximately Poisson distribution. However, such is not the case. Why? Because although the events all have small probabilities, some of their dependencies are too great for the Poisson distribution to be a good approximation. For instance, because of the conditional probability that flips 2 up to k plus 1 are all heads, given the flips 1 up to k are all heads is equal to the probability that flip k plus 1 is a head. It follows that probability of so hi denotes the event that flips I. So this is from 1 up to 1 plus k minus 1, which is a k, right? So this is so h1 denotes k heads, h2 I guess is k plus 1. So probability of this conditional probability equals p, which is far greater than the unconditional probability of h2. The trick that enables us to use a Poisson approximation is to note that there will be a string of k consecutive heads, either if there is such a string that's immediately followed by a tail, or if the final k flips all land on heads. Consequently, for I equals 1 up to n minus k, let ei be the event of flips I up to I plus k minus 1 are all heads, and the flip I plus k is a tail. Also let event n minus k plus 1 be the event that flips n minus k plus 1 up to n are all heads. Then we have probability of the event I equals the probability of k times 1 minus p, right? Because this one is a tail, 1 minus p is a tail. So we have p heads and 1 tail. Then probability of event of n minus k plus 1 would be p to the, so this is for I less than or equal to n minus k. So this one will be p to the k. When p to the k is small, each of the events ei has a small probability of occurring. Moreover, for I not equal to j, the events ei and ej refer to non-overlapping sequences of flips. Then this probability will be this. If they refer to overlapping sequences, then the probability goes 0. Hence, in both cases, the conditional probability are close to the unconditional ones, indicating that n, the number of events ei that occur, should have an approximate Poisson distribution when the mean calculating is this, n minus k times p to the k times 1 minus k plus p to the k, right? So the two situations. Because there will not be a run of k heads if and only if n equals 0, the preceding gives probability of no head strings of length k, no head strings of length k equals to n equals 0, which is e to the power of this. All right, that's enough for this. Let's see if we'll have more examples. Let's read this. Another use of Poisson probability distribution arises in situations where events occur at certain points in time. One example is to designate the occurrence of an earthquake as an event. Another possibility would be for events to correspond to people entering a particular establishment, like a bank, post office, gas station, and so on. And the third possibility is for an event to occur whenever a war starts. Let us suppose that events are indeed occurring at certain points of time. And let us assume that for some positive constant lambda, the following assumptions hold true. 1, the probability that exactly one event occurs in a given interval of length h is equal to lambda h plus O of h, where O of h stands for any function f of h for which limit of f of h divided by h when h equals 0 equals to 0. For instance, f of h equals h squared, whereas f of h equals h is not, right? That would be 1. But with square, yes, because h squared divided by h with h, when h goes to 0, h goes to 0. Second, the probability that 2 or more events occur in an interval of length h is equal to O of h. Third, for any integers n, ji, j12 to jn, and any set of n non-overlapping intervals, if we find ei to be the event that exactly ji of the events under consideration occur in the i's of these intervals, the events ei up to en are independent. So this is good to know, right? You may have some homeworks. Let's see. So the preceding discussion explains why a Poisson random variable is usually a good approximation for such diverse phenomena as the following. 1, the number of earthquakes occurring during some fixed time span. The number of wars per year. The number of electrons emitted from a heated cathode during a fixed time period. The number of deaths in a given period of time of the policyholders of a life insurance company. Good to know. Okay, this is the example. 7E. Suppose that an earthquake occurs in the western portion of the United States in accordance with assumptions 1, 2, 3, with number equal to and with one week as the unit of time. That is, earthquakes occur in accordance with the 3 assumptions at a rate of 2 per week. A. Find the probability that at least 3 earthquakes occur during the next 2 weeks. B. Find the probability distribution of the time starting from now until the next earthquake. This is an interesting question, huh? So let's see. So we have, next 2 weeks. So next 2 weeks, at least 3 earthquakes for next 2 weeks, which is 1 minus 0 earthquake, 1 earthquake, and 2 earthquakes. So plug in Poisson distribution and equals 0, and equals, I equals 0, I equals 1, I equals 2. Then we get this number. Then the second part is find the probability distribution of the time starting from now until the next earthquake. So let X denote the amount of time until the next earthquake, because X will be greater than T if and only if no events occur within the next T units of time. So we have probability of X greater than T equals the probability of no earthquake until next time, which equals to plug in T for I, which is equals to e to the negative lambda T. So the probability distribution function f of the random variable X is given by f of T equals the probability of X less than or equal to T equals 1 minus probability of X greater than T is 1 minus this value, 1 minus this, 1 minus, because we're given 2, right? A rate of 2 per week. So that's 1 minus e to the negative 2t. If X is a Poisson with a parameter lambda, then we have probability of the next one, right? And the probability of X equals I, plug in, simplify, we get lambda divided by I plus 1. Starting with 0, we'll plug in 0 for Poisson distribution, we get this. So we have 0, we get this. 1, we get lambda times probability of, so this is e to a negative lambda, and lambda times e to a negative lambda. Then lambda over 2 times this, so on and so forth. So for I plus 1, we get lambda divided by I plus 1 times probability. So this is recursive. So we can use a module to compute the percentage probability for the. Okay, so let's see 7F. Determine probability of X less than or equal to 90 when X is a Poisson with a mean 100. Determine probability of Y less than or equal to 1075 when Y is a Poisson with mean 1000. Just plug in, right? Use Poisson. Oh, this is use Poisson calculator. All right. So that's it. So next time we're going to talk about geometric random variable. All right. That's Poisson. Okay, anyone has any questions? So the big important thing is the variance and expected values are all numbered. If we know it's a Poisson distribution, oh, you know, I like to use the distribution. I actually say random variable, but it's the same thing, all right? Other textbooks would call Poisson distribution, but this textbook called Poisson random variable. All right, midterm is online. All right, so let's talk about midterm. Midterm is when? Midterm is on 21st, right? Yes. Midterm is on 21st. And yeah, it should be easy. You know, if you have done class presentations, if you have done some homework, it's very basic, no surprise. It's very basic. And some questions are very similar to the examples on the textbook. Zakia, only final is in person, all right? The final, the school is supposed to assign us a room. When we get a room, when I get the final time, I will announce it. But so far, I haven't got anything about the final yet. So every class, the final should be supposed to be on campus. But because this is an online class, the midterms, homeworks, all online. You're welcome. All right, let me stop.